Hi everyone, I just wanted to go over section 4.1 and maybe section 4.2 as well, because I was planning to make a meeting today, to host a meeting, a WebEx meeting, but for technical issues the message or the announcement didn't go through. So no problem. Anyways, I'm preparing a video about 4.1 and 4.2, and I hope I cover the material in this video. I mean the two sections. And if you have any question, please contact me and let me know, and you can join us during the office hours or by email. Just let me know. And on Thursday we'll meet, and I will try to send the announcement or invitation earlier than this time. So chapter 4 is about probability. We start with 4.1 is and we talk about basic concepts of probability. Now in probability theory we are interested in the question of what are the chances of some event to occur. So the occurrence of some event is very important. For example, we may ask, what is the chance of winning the lottery? What is the chance of raining today, or snowing in December, or getting A in some class? So all these are questions asked about probability or chances or possibility. That's what we mean by probability in general, in the common sense. But here in this section we'll focus on studying probability mathematically, and we try to deal with formulas and study the basics of this vast theory. The basic elements that we need to know are the following. Event is any collection of outcomes of a procedure or experiment. For example, if the experiment is about rolling dice, then the outcomes are, we put them in a set notation: 1, 2, 3, 4, 5, 6. The uppermost face will give us one of these 6 numbers when rolling a dice. And then if we are interested in the even numbers here are 2, 4, and 6, and they form a set, another set. It's 2, 4, and 6. This is the set of even numbers, and this is called event. Event is a subset of all outcomes of some experiment. Now all of the outcomes are called, the set of all outcomes is called the sample space. So the sample space is the set of all possible events or outcomes, all possible outcomes. And the event is subset of that. As you can see, 2, 4, and 6 is a subset of the sample space. And for sample space, we usually use one of the following two notations, either letter S or omega, but in our course we use capital S to denote sample space, and for events we usually use one of the English alphabet capital letters A, B, C, D, etc. So event is some outcomes that are have some interest for us, and the sample space is the whole set of outcomes, all possible outcomes. For example, if you toss a coin, you may get either head or tail. So all possible outcomes are head and tail. So this is the sample space. What can you give me an example of an event of interest? you may say that I'm interested in seeing the chances. What are the chances of getting hit? So that is a subset of the sample space, and it's called event. So event is a subset of the sample space. Simple event is an event that cannot be broken down into simpler events. For example, here we can't break down the event A into other events. If we have 3 births, one of the good tools to and powerful tools to find all elements of or sample space of some experiment is to use tree diagrams. For example, if we have 3 births, we want to see all possible outcomes here. This is the sample space S. In order to make sure that we got all the outcomes correctly, we use tree diagram. So the first birth can be boy or girl. If the first one is boy, then the second one can be boy or a girl. If the first one is a girl, then the second one can be a boy or a girl. If the first one, second one are boys, the third one can be a boy or a girl. If the first one is a boy, second one is a girl, the third one can be a boy or a girl, and so on. So this is called tree diagram, and it helps us in finding all or determining all possible outcomes. Now, what are the possible outcomes? So you can see BBB, 3 boys. We may get 3 boys, as you can see here. So we can use a small letter because we are talking about elements in the set. So you can, I may change these into little b, little g, and so on. But don't worry about this. Okay, so I just changed them because when we have a set, this is called set, and we have elements inside the sets, and there's comma that separate every 2 elements, and the elements in the set are denoted as small letters, or they can be numbers, letters, anything. And we call the whole set, for example, a capital letter. We use capital letter to name the set, and we use small letters for the elements of the set. Okay, so here we have one of the outcomes is boy, boy, boy. We got 3 boys. Or on this branch, boy, boy, girl. Or we may have boy, girl, boy, or boy, 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 or boy, girl, girl, and so on. So we can find all the possible outcomes, as you can see here in this method. So those are the outcomes. Okay. Now, if we are interested in the event that having, for example, here example of event 2 boys and 1 girl. So 2 boys and 1 girl, as you can see here, we have, this is the sample space, and we have 2 boys and 1 girl here, here, and here. So we have 3 outcomes, as you can see. And those are simple outcomes. We can't divide them into more outcomes. Okay, so that's what we mean by event and its relationship with the sample in general. So let's take an example. We want to identify sample space S, and a simple event, let's call it A or E, in each of the following cases. Getting ahead, this is the event. This is the event A. So the event A consists of head. So we just write it as a singleton or a set that consists of 1 element. And as I mentioned, you may write it, use little small letter or capital letter. It's up to you. So let's use small letter here, head. If someone wants to use capital letter, they are welcome. Now, tossing a coin, what are the all possible outcomes? The all possible outcomes are heads and tails, head or tail. Some people want to write it this way. That's okay as well. Okay, so this is sample space. This is an event of that sample space. And this event is simple. Now, getting a number that's more than 4. So number more than 4, that's the definition of the event, for example, A. And rolling a die once. So in rolling a die once, we get the numbers. What are the all possible outcomes? 1, 2, 3, 4, 5, and 6. Now getting a number that's more than 4, 5 or 6. So those are the two numbers. So this is an event and this is the sample space. Two results are same if you toss two coins. We're tossing two coins, so we get, for the first coin we get head or tail. For the second one, if the first one is head, the second one can be head or tail. If the first one is tail, the second one can be head or tail. So all possible outcomes are head, 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 tail, tail, head, tail, tail. So these are all possible outcomes. We call them S, or sample space. Tail, tail, head, tail, tail. Okay. Now, two results are same. This is the event A or E or B or any, you can use any letter. Same, we have head, head, or tail, tail. So this event consists of head, head, or tail, tail. Okay. Now we have notation for probability. We use for probability the letter capital P, and for events A, B, C, etc., those capital letters. And P of A means probability of an event A. And usually when we compute this, this is a number. This is a number, and we obtain this number by applying some rule. We'll talk about it later. And this number should be between 0 and 1. And sometimes we are interested in finding the complement of some event. Complement of an event is written A bar, and that's read complement of an event. What do we mean by complement of event? For example, here, look at this event. The event consists of head, head, tail, tail, same outcomes. Now, or in the first, the first toss and the second toss. Now, what is the complement of this? The complement of this is a complement. What are the other elements that belong to the sample space but that do not belong to the event? We have head, tail, tail, head. So head, tail, tail, head. This is the complement of A. Some people prefer to use C instead of the bar and to denote complement, but in our book we use bar to denote the complement. So the complement are all elements that belong to the sample space, but they do not belong to the event. Now, and we can find the probability of the complement using some rule. Okay. Now here, if we look at this diagram, we have the probability of that some event is impossible. For example, in rolling a die once, what is the probability of getting a number that's greater than 6, like 7? That's impossible because the numbers are from 1 to 6. So that's probability of getting a number that's greater than 6 is 0, and that's called impossible event. What is the probability of getting a number from 1 to 6? It's 100%. When you roll a die, then for sure, or for 100%, you are 100% sure that you will get a number from 1 to 6, and that's called certain event. And then in the middle, we may ask, what is the probability of getting head after tossing a coin once? head has chance of 1/2 because we only have two outcomes, head or tail. So 1/2 for head and 1/2 for tail, or 50 for head and 50 for tail. So equal chances. It's unlikely if we get a probability here very close to 0. It's unlikely. Very close to 1, that's likely. In the middle, that's the in general when we deal with two outcomes or half outcomes. Okay, now we come to the basic formula for probability. This is the basic formula for probability. Probability of an event is number of elements or number of ways A can occur, or number of elements of the event over number of elements of the sample space. So S is number of elements in an event, and S is number of elements of the sample space. Okay. We usually round the probability to 3 significant digits. Okay. Now let's take an example. When a couple have 3 children, find the sample space first and the following probabilities. So let's start with the experiment. Experiment consists of 3 children, and we are choosing from them. I mean, when a couple have 3 children, find the sample space. The 3 children can be the first kid, or the first kid can be boy or a girl. The second one can be boy or girl. The third one can be boy or girl. So we may get, that's the sample space, boy boy boy, or boy boy girl, or boy boy, this should be girl, boy girl boy, boy girl girl, and here boy or girl boy boy, girl boy girl, and girl girl boy, girl girl girl. How many outcomes? We have 1 2 3 4 5 6 7 8. There is another way to do that. How many outcomes here for the first first time we choose? It's 2 outcomes. Here, how many outcomes? 2 outcomes, because they are only boy or girl. 2 outcomes. Here, 2 outcomes. Now multiply them, you get 8. So we have 8 outcomes here in the sample space. That's number of elements in the sample space. Now this is the sample space, and we want to find the possibility or probability of getting exactly 1 girl. Exactly 1 girl can occur here, here, and here. So that's the event. For part A, the event, let's call it A. The event is boy boy girl, boy girl boy, girl boy boy. And we want to find this probability. Probability of the event A is number of elements of the event. We have 3 outcomes. And over number of outcomes of the whole sample space, we have 8. So 3/8 for part B. And actually here I meant by element outcomes. Okay. Now for part B, all boys, all are boys. We only have 1 outcome. So let's call this event B. B consists of only 1 element, boy boy boy, and probability of getting of all the kids are boys is 1 out of 8 outcomes of the sample space. Now part C, no boys. No boys, that means all of them are girls, and that happens only once. So that is, let's call this C. The event C consists of 3 girls, and the probability of C is number of elements of that, or number of outcomes in that event. It's just one, girl, girl, girl. This is just one choice out of the all number of outcomes in the sample space is 8. So that's the probability. As you can see, if you look at these probabilities, as you can see, they are less than 1 and greater than 0. And that's the case. Okay, law of large numbers, we usually, when we toss a coin, for example, 10 times, it need not be the result boy, girl, half. We may get, for example, boy 4 times and girl 6 times, or so on. So this is just an approximate. If we repeat the experiment enough time, I mean, for example, 100 times, 1,000 times, million times, we find that these probabilities tend to be close to each other, 50-50. Okay, now significant probability, for significant results, if the probability is less than or equal to 0.05, then it's significantly low number of success. If its probability is greater than this, then it's significantly high. Okay, now some rules or some properties of probability. We say that P of A is probability of an event A. Probability P of A complement is probability of the elements or that of event A does not occur. And we need to notice that probability of an event plus probability of its complement is equal to 1. And this is very powerful rule in finding probabilities, I mean computational probabilities. For example, if you are tossing a coin, you may get, for sample space, you will get head or tail. What is the probability of head? It's just 1/2. Probability of getting tail, it's 1 out of 2. Now, what is probability of head plus probability of head complement? I mean by head complement, tail, right? So that's 1/2 plus 1/2, which is equal to 1. And that means this shows our result is, this is just an application on our result. Okay. That was 4.1. Now let's go to 4.2. Now we have some rules. Now we start to deal with rules that to help us to find probabilities in certain situations. We have addition rule and multiplication rule. Now, probability that either event A occurs or event B or both of them occur, that's the probability of A union B. This is read union or or. When you see union, that means the occurrence of the set A or event A, or if occurrence of the set B or event B, or both of them. So we usually find this keyword. The keyword here is or. Or means union. So we can replace this with this notation, this symbol U. And what is the rule that we use? We use the following rule. Probability of A union B is probability of the event A plus probability of the event B minus probability of the intersection. The intersection is A and B, and the word and means intersection. So or is union and is intersection, and we usually use these notations. This is union, this is intersection. Okay, so this is the rule that we usually apply. If the two events are separate or disjoint, then this probability is 0. We don't need this because A is not intersected with B, so we just ignore this part. Okay, for example, look at this figure here. This is called Venn diagram. As you can see, there's something in common between the two events A and B. This is event A, this is event B. So we have something in common here. So they are not disjoint. So we need to consider this part, probability of A and B. And the idea here is that we want to find probability of the union. Everything, the union means everything here in A and in B. Everything here in A or B, or in both of them. But if we consider A, probability of A, this is probability of A. This gives us this probability of elements here. And then probability of B, this will give us probability of all elements here, right? But as you can see, we considered this area twice when we considered probability of A, and then when we considered probability of B, and that will not give us an accurate result. So we need to subtract one of these areas because this is overlapped. This is considered once with A and then considered with B. So we just want to consider it once. So we take probability of A, everything here, plus probability of B, but this is now counted twice. This is counted twice. So we just subtract one of them. What do we mean by one of them? That means probability of A and B, the occurrence in the same time, A and B. So we just subtract this as we did here in this formula. As you can see, we subtracted the intersection. Now, if they are disjoint, this case is called mutually exclusive events, and in this case we only need to find the sum of the two probabilities, probability of elements here plus probability of the elements here. We don't need to subtract the intersection because we don't have intersection. This is the intersection. If we don't have intersection, that means we don't need to subtract probability of A and B. Okay, good. Now, some rules. Probability of A plus probability of A complement is 1. We talked about this. And then from this we can find other probabilities. For example, if I know probability of A and I want to know probability of A complement, then I apply this rule, this basic rule, to find that. So we know that probability of A plus probability of A complement is equal to 1, but I know probability of A. So we want to solve for probability of A complement. This is unknown. So probability of A complement, we just bring this to the right hand side, and that means we subtract it from 1. I mean to subtract probability of A from both sides. And that's it. So we got this rule here. Same thing happens when we deal with probability of, this way, this formula. Same thing if we know the probability of the complement and we want to find probability of A, we just write 1 minus probability of A complement. Okay. Now let's take an example. For this example, we want, when tossing 2 6-sided dice and summing the sides that are face up, let A be the event, the sum is greater than or equal to 10. Now we want to list the sample space for the event A. What is the sample space? Okay, so we are tossing 2 dice, 2 6-sided dice. So in this case, we can make a table that will make computations easier. So for the first die, we have 1, 2, 3, 4, 5, and 6. And for the second one, we have same thing. Okay, and then we may get 1, 1. When we toss the 2 dice, we may get number 1 on the first uppermost face and 1 on the uppermost face of the other die. So we get 1, 1, or 1, 2, or 1, 3, 1, 4, 1, 5, or 1, 6. Or 2, 1, 2, 2, 2, 3, 2 with 4, 2, 5, 2, 6, or 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. I will complete this. So these are all possible outcomes. This is the sample space. So these are all possible outcomes. Now we want to determine the event A. The event A says the sum of the elements is greater than 10. Sum of the numbers, the appeared numbers, after tossing 2 dice, we get numbers, and we will, on each die we have numbers from 1 to 6. So if we observe that after tossing the coin, rolling the dice, and then we determine the sum of the 2 numbers, the appeared numbers. Now we want that number. The event says that the sum is greater than or equal to 10. Now, as you can see, this sum gives greater than number that's greater than or equal to 10. This is greater than or equal to 10. This is equal to 10 actually. And here this is greater than 10. This is greater than 10. These are the only outcomes that give us the event A. Because if you choose this, the sum is 7. And here 5. Here 2, but those do not belong to the event, because the event deals with the numbers whose sum is greater than or equal to 10. So how many elements are there? We have how many outcomes of the event A? We have 6 outcomes. How many outcomes for the whole experiment? We have 6 numbers here, 6 numbers here. 6 times 6 is 36. So over 36. So it's 1/6. Using the calculator, we find that this can be approximated to 3 decimal places, 0.167. So the possibility percentage is 16.7%. Now, what is probability of A complement? Instead of finding, now in order to determine A complement is this. Everything here, this is the complement of A. This is the complement of A, but it's not. If you don't want to count all these numbers and divide by the total number, you can apply the rule that says probability of A plus probability of A complement is 1. And from these, we know that probability of A, and we want to find probability of A complement. I want to use this notation. So we know probability of A, and we want to find probability of A complement. So let's use the third rule here. So probability of A complement is 1 minus probability of A. That's 1 minus 0.167. So this gives 0.833. Now let's take another example. Here we have a table. We're given a table, and we will use these data to find the following things. If one subject is randomly selected, here we have subject use. We choose some people. Some subject uses drugs. And some other subjects don't use drugs. And we made some tests. We found that positive test results, drug use is indicated here. 44 true positive, 90 false positive. For example, for this one, we test those people here, those don't use drug, but 90 of them give positive, while they are assumed not to use drugs, and so on. Now here, false negative, so it's negative. Drug use is not indicated. So when we test them, we got negative result when we test those people while they are drug users. Okay, so for this example, if one subject is randomly selected, find the probability of selecting a subject. We want to find probability of selecting subject who had positive result. Probability of positive. What is the probability of positive? Positive in this column, positive test in this column. So how many people are there, whether they use drug or they don't use drugs? So we need to find the sum. The sum is 134. 134 over the total number. We need to find the sum of all these numbers. Here we have 50 on this row. On this row we have 950. So the sum is 1000. And here this is 134. This is 866. The sum is 1000. So 134 out of the total number of people in this experiment is 1000. So that's 0.134, or in percentage 13.4%. Now the second question: if one subject is randomly selected, find the probability of selecting a subject who had negative tests, or probability of negative tests, or means union. Used drugs. Used drug. I just want to write. Let me write a drug here. Union, that's the probability that we want to find, because the key word here is the word or, and that means we use this notation for or, union. Okay, and using the rule we have, if you remember, are they disjoint or not? They are not disjoint. We can get negative result, but while that person uses drug. All right, so we have probability of negative plus probability of the second one, drug, the second event, used drug, minus probability of negative, and this is and use drugs. What is probability of getting negative? Negative is here. This is probability of negative. The sum is 866 over 1000, plus probability of using a drug. People who use drug are here, all those people. It's 50. So we have 50 out of 1000 minus the negative and used drug. Used drug is here and negative is here, so the intersection is this. So the intersection of this and this is this number, 6. So minus 6 over 1000, and computing this using a calculator we get 0.91, or 91% if you want to use percentage. Okay. Now if we want to ask, would it be unusual to select a subject who had a negative test result or used drugs? Since we got 91%, and that's greater than to 5%. If it's greater than 5%, I mean 0.05. If it's greater than 0.05, that means it's not unusual. That means it's usual. Okay. Now that was the sum, the addition rule. This is called addition rule because we added probabilities. And here we have multiplication rule. For multiplication rule, we need to worry about concept of dependence and independence. And we say that two events are independent if the occurrence of one does not affect the occurrence of the other. For example, when a baby is born, it's a girl. This is event A. When a second baby is born into a different family, it's a girl. Those are completely different and independent. So the occurrence of a girl here does not affect the occurrence of a girl for the other family or for any other family. So those are completely different and independent. There's no relationship between them. We just say they are independent events. But for dependent events, when a day of a week is randomly selected, it's Saturday. So we started with Saturday for event A, and then when the second different day, we excluded Saturday now for event B. When a second different day of the week is randomly selected is Monday, and here those it was our choice here is affected by the occurrence of A. Why? Because in first selection we got Saturday. That's the event A. So we already chose Saturday. On the second choice or event, we have a different day. So if the first one is Saturday, we should consider the rest of 6 days: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday. So all these other days, we can't use Saturday again. So the choice of B is affected by the choice of A. We need to avoid Saturday, so that means the two events are dependent. Okay, if we know that the two events are independent, then probability of A and B, if we have the keyword and here, then we just use multiplication. We multiply the two probabilities. If they are dependent, then we need to use what is called conditional probability. We will talk about it later. Okay. Now sampling. If we have sampling with replacement, for example, you have a box and it has, for example, 2 red balls, 3 green balls, and 5 black balls, for example, and you want to pick one ball at random, then the selection here, if you do that selection with replacement, you want to pick 2 balls, or the first ball, then look at it and then choose the second one. If that happens with a replacement, you just pick one ball and then return it, and then you pick another ball. So if that happened with replacement, selections are independent events. If the sampling happens without replacement, I mean, for example, you choose the first ball and it was red, and then you throw it away and you choose another ball, the probability of the another ball will be affected because we have less or smaller set, right, to consider, and the sample space will be reduced by 1, and that will affect the probability. That means we have selections are dependent in this case. So if the sampling happens with replacement, then the selections are independent, and if they are if the sampling happens without replacement, then selections are dependent. Now, for example, if we have, for example, 3 babies are born in different cities. In event A, the first baby is a boy, and the event B, the second baby is a boy, and the third baby is a girl. Then we want to find the probability of getting a boy in the first, from the first event, or in the first, for example, city, and then boy, and then girl in our third selection. So probability of A, and we use and here, B and C. So since they are independent events, we need to apply this rule. We just multiply the probabilities. Probability of getting a boy is 1/2, because we may get boy or a girl, so 1/2 for boy, and for the second one 1/2, and for the third one girl is 1/2. So we just multiply them to get the probability of getting boy, boy, girl. Okay. Now we have example 3 here. A pop quiz consisting of true-false question and a multiple choice question. Okay, with 5 answers. The multiple choice question consists of 5 answers. The answer key is true and C. So that's the answer key, true and C. So we want to find the probability of some randomly guesses for both answers. Both answers will be correct. So find the probability of someone randomly guesses for both answers. both answers will be correct. So that's want to find this probability of getting true on the true false problem and C on the multiple choice problem. So this is the probability that we want to find. So let's make a table. We either use a table or tree diagram. So let's do tree diagram. So first we may let's start with the true false problem. We may get true or false answer, and then after that let's go to the problem, the multiple choice question, and see if we get true on the true or false. We may get one of the answers A, B, C, D, or E on the multiple choice problem. If we get false answer, if we choose false answer in the true false question, then we may select A, B, C, D, or E for the multiple choice question. Okay, now how many outcomes are there? As you can see, true and A, true and B, true and C, true and D, true and E, then false and A, false and B, false and C, false and D, false and E. So this is the sample space. The sample space consists of all these elements. Now we are interested in one answer, true and C. So true and C, this is true and C. It's one out of how many outcomes? One out of how many outcomes are there? For the first choice, or I mean for the true false question, we have 2 outcomes. For the multiple choice, we have 5 outcomes. 2 times 5 is 10. That's the number of elements in the sample space. Or you may count 1, 2, 3, 4, etc. So the answer is 1/10. Or we can use the multiplication rule. How to use the multiplication rule? We want to find probability of T and C. That is probability of T times probability of C, because those are independent. Your choice of true, for example, is not affected by the choice of C for multiple choice problems. So those are independent. Now what is probability of T, of choosing true? That's 1/2, because we only have 1 outcomes for true or false, just 1/2, times probability of C. C is 1 out of how many outcomes? 5 outcomes, or 5 choices, and then we multiply them to get 1/10. As you can see, we got the same answer. Now this example, we have 50 test results from the subject who uses drugs are shown below. Positive test results 44, negative test results 6. If 2 of these 50 subjects are randomly selected with replacement, find the probability that the first selected person had a positive. So probability of positive and or you may just write and here. The second selected had a negative result. Okay, so that happened with replacement, and that means they are independent. So we just find probability of positive times probability of negative, of selecting a person or subject with negative result. Probability of positive, we have 44 out of 50, because that's the sample size or the sample space, times probability of negative, we have 6 out of 50, because it happened with replacement. We just choose the first one was positive, we have 44 probability of possibility out of 50. And then for the second one, we still have 50, because when we choose the first person, we asked him, after checking that person or subject, we asked him to go back to that set, and then we choose another one to see if that subject is positive or negative. So that means we still have same sample size, because the selection was randomly and with replacement. So we just multiply these two to get 0.1056. We can just round it to 106 or 10%, 10.6%. Now for part B, the selection happened without replacement. Now without replacement, that means when we choose the first subject and check, we ask that subject to set aside, and then we choose another person from the set that's reduced by 1. So for the first one, probability of the first is positive and the second is negative. In this case, without replacement, is probability of positive times probability of negative. We still have independent answer, because if the first one is positive, the second one is not affected by whether the first one is the choice. But here, since it's with replacement, the denominator will be affected. Okay, so we still multiply the probabilities, but probability of positive is 44/50. And then we want to find probability of negative. What is the probability of getting subject that was negative in the second stage of the experiment? The first stage is to choose one and to check if that subject is positive. That was 44/50. Then we ask that one who's already chosen, selected, to set aside, and we paid attention to the rest of the people. How many people are there? We have 49 people left. So we choose one and we see if that subject is negative. We only have 6 with negative, so we just write 6/49, the denominator reduced by 1, and then we do this multiplication to get at random, approximately 1.8 or 10.8%. Okay. Now here we have an example of the probability that student passes math is 0.76. Let's write this probability. Probability of passing math is 0.76, and probability of passing English is 0.83. The probability of that student passes both is 70. Math and English is 0.7 or 0.70. Now we want to find what is the probability that that student passes at least one subject. What do we mean by at least one subject? Mathematics or English, or both of them. So one of them or both of them. When you read at least, this is keyword. At least means union, means or. Math or English or both of them. So we write the probability this way. Probability of math or means union. So we use this simple union, that means or you just write or. English, that's probability of math plus, that's the addition rule, probability of English minus probability of math and English. Because we have something in common here. We have intersection. We may have some student who passes math and English together, both of the courses. So we need to subtract that. So this is the rule, the addition rule. Now what is the probability of math? It's 0.76. What is the probability of English? Passing English is 0.83 minus both is 0.70, and using calculator we get 0.89. Okay. Now problem 6 here. We have sample of 200 tourists who visited Chicago during the past year. The survey, so this is the sample size or sample space size. The people who visited Illinois, they traveled, we have 125 of them went to Sears Tower, 100 went to Wrigley Field, and 70 visited both. The question is, what is the probability of selecting a person at random who visited Sears Tower or, this is a keyword, Wrigley Field? So that means we want to find probability of Sears. Let's use the letters S to denote this, and the letter W to denote Wrigley Field. So or means union, and then Wrigley Field, that's union. Okay, so we apply the rule, the addition rule. We have probability of S of visiting Sears Tower plus probability of visiting Wrigley Field minus probability of both S and Wrigley. So probability of visiting Sears Tower is how many people? We have 125 who visited Sears. Out of how many? Here we don't have probabilities, we need to find the probabilities. Out of 200 plus probability of the people who visited, or selecting one person who visited a Wrigley Field. How many people visited this site? We have 100 out of 200, the total people, minus both. How many people visited both? We have 70 visited both out of 200. So we should find the probabilities here, and then using calculator we get 0.775 or 77.5% of the people who visited the Sears Tower or Wrigley Field. Now the last example in this lecture is the following example. We are given a table that consists of survey that represents a survey that conducted to investigate the relationship between preferences for television, radio, or newspaper for national news and genders. Here we have genders, and here we have three national news resources, and then we find the sums. The sum of this row is 760, here 560. The sum of columns, as you can see here, and the total sum of the people who were engaged in this survey is 1320. Now we want, if one individual is randomly selected, we want to see what is the probability that the individual prefers radio. I want to find probability of radio. That's how many people prefer radios. We have 450, that's the sum, over the total number. The total number is 1320. So the probability is 0.341. As you can see, the probability is always between 0 and 1, or from 0 to 1. It can't be negative, it can't be above greater than 1. So if you compute the probability and you get number greater than 1, like 2, that means you did a mistake. Now, for example, here in this example, some people may just write 100. They think that this is probability. 70. Those are not probabilities. Those are numbers greater than 1. Okay. So here, what is the probability for part B that the individual is a male and prefers radio? Male and prefers radio. That means I write male, probability of male, and prefers radio. So that's how many? We have 175 out of the total number is 1320, and that is 0.133 using calculator. For part C, what's the probability that the individual is a male, still have male, or individual prefers radio, or so probability of male or radio, use radio, or prefers radio. I wrote and union, it should be union. This is or. Okay, so in this case we apply the addition rules. Probability of male plus probability of person who prefers radio minus probability of male, the person is male and prefers radio. So what is probability of getting a male? So how many males are there? We have 760 over 1320 plus. What is the probability of watching or following radio news? We have 450 out of 1320 minus probability of male and watch radio or follow radio news, 175. This is the intersection between radio and male, 175 over 1320. So using calculator we get 0.78. Now part D, what is the probability that the individual prefers TV or radio? Probability of TV or radio. And for or we use union. So this is also additional rule, probability of TV plus probability of radio minus probability of TV and radio. What is probability of watching or preferring TV? For TV we have 395 persons out of 1320. And for probability of getting someone who prefers radio, how many people are there? We have 450 out of 1320. Minus probability of TV and radio, we don't have any intersection between TV and radio, so that's 0. So computing this, we get 0.640. That's the probability of getting someone who prefers TV or radio.